The solutions to the hydrogen atom Schrodinger equation are one of the most complicated systems that we can actually solve exactly. And we've discovered that their wave functions can be labeled using three different numbers, n, l, and m. Well, these three numbers are numbers that we're going to equate with quantum numbers. They are quantum numbers. And let's talk a little bit about where they come from and what they designate, what they signify about different wave functions. Okay, our quantum number n, all right, what is that related to? Well, it's related to, if you will, the eigenvalues of the Hamiltonian operator. And we have found that those eigenvalues can be written as follows. The e sub n is equal to minus m e to the fourth divided by 8 epsilon squared h squared n squared. So we can see that this n appears in the denominator. We've further shown that this can be written more compactly as a multiple of the Hartree energy, or 1 over 2n squared times the Hartree. So the n here is something that relates to the energy, and it labels the various eigenvalues of the energy, and for this reason we call it the principal quantum number. All right, so it is, if you will, the king of the quantum numbers for hydrogen. We then have the quantum number label L, and we know that this is associated, for example, with the angular momentum squared. And when we solve the equation for angular momentum, the eigenvalue equation for this, we find that its eigenvalues now can be labeled as follows. They're h bar squared times L plus 1. And so this is basically the result of doing the eigenvalue equation for L. So for this reason, little l is called the angular momentum quantum number. Now that leaves us one quantum number left, and that's m, and it turns out that this is related to the eigenvalues of the LZ operator. And in an earlier video we saw that these eigenvalues actually could be related as m times h bar. Okay, and since we've already used angular momentum in a title, it turns out that these quantum numbers are given the designation magnetic quantum numbers, for historical reasons. All right, so what we want to do now is explore what possible values these various quantum numbers can have. And we know that the principal quantum number, it can't be 0 because that would make the energy levels blow up. They would diverge to negative infinity. So the principal quantum numbers can have the values 0, 1, 2, 3, and so forth. The L quantum numbers are limited in turn by the N quantum numbers. And in fact, their values, they can start at 0 and they can go all the way up to n minus 1. All right, and that came about from our solutions to the Schrodinger equation as well. Finally, we found that the magnetic quantum numbers are limited by L, and they can have values 0, plus or minus 1, plus or minus 2, up to plus or minus L. And this came about when we were talking about the solutions as being derivatives up to power m, that is the mth derivative of a function that had a polynomial term of no higher value than L, that this was what limited the m values. So we can say that n values L, n constrains L constrains m. So these are all the possible quantum numbers that we can have. Now I would also suggest that it's useful to indicate what parts of the solutions these things give rise to or play a part in. N and L play a part in determining the radial wave functions, while L and M play a part in defining the angular wave functions. So they both have a very distinct role, and L is sort of the bridging quantum number that has an impact on both the radial and the angular parts of the wave function. All right, so what we'll find actually is the angular momentum of an atom, the angular momentum that is encapsulated in L, if you will, is actually an extremely important quantity, and it's one that we will use to specify and to characterize the various states that we find in these atoms. Now, I mentioned earlier that the total degeneracy of the hydrogen atom wave function, or the nth wave function, degeneracy of E sub n was equal to n squared. Where does this come from? Well, let's imagine using these limiting values that for any value of n, so I've got some value of n, how many different values of L can I have? Well, I can add values of L from L equals 0 to n minus 1. That's the maximum value of L that's possible. All right, now the total number of states within each L is given by the number of different m values that one can have. And if one counts them up, we would have 1 for L, m equals 0, plus 2, plus 2, plus 2, all the way up to L. So that means that we would have 2 times the total number of L plus 1, or 2L plus 1 different values of m correspond to each value of L. So to count up all of these states, I would have 2L plus 1 adding up from L equals 0 to n minus 1. Okay, so how is this going to work? Well, I'm going to have twice the sum, and since L equals 0 doesn't contribute to the sum, I can do this sum from L equals 1 to n minus 1 of L. And then I'm going to also have a sum from L equals 0 to n minus 1 of 1. Okay, so there's a total number here of n values, so this sum is just going to be equal to n. What about this sum? Well, whenever we add consecutive integers together, there's a famous formula that we add, say, the numbers n up to capital N, that their sum is going to be equal to n times n plus 1 over 2. So when I plug that into this, I'll have twice times the sum of n minus 1 times n minus 1 plus 1 over 2. The 2's cancel. I'm going to add now to this a value of n. So I'll end up having n times n minus 1 plus n, or n squared minus n plus n squared. So I think you can see that just adding these states up always will give us the result n squared, and that's the degeneracy of the nth energy level of the hydrogen atom. Now, the last question I might want to ask is, we've said that the L influences these functions, these radial wave functions R sub nL. How does that work? What does that mean? Well, I want to look at, and I'm going to draw rough hand, 3 different sketches of the radial wave functions corresponding to n equals 3. And these 3 sketches will correspond to n equals 3 and L equals 0, 1, and 2. So for n equals 3, L equals 0, what will I have? Well, it turns out when I graph this function, it will look something like this. Okay, when I graph the function for n equals 3, L equals 1, it looks a little different. It looks like this. And when I graph the function for n equals 3, L equals 2, it looks even different still. It looks like this. All right, so we can see that, in fact, L has a profound influence on the shape of the radial wave function. So it's not just a cosmetic thing that we're talking about. It's a real difference. Another point that I will make, and we'll reinforce this in a later lesson, is that L also impacts the number of places where the radial wave function crosses the x-axis. Here it crosses twice, here it crosses once, and here it doesn't cross at all. So that influence of L will have some impact, at least, on the form and the shape of the wave functions that characterize the hydrogen atom.